So in this instructional video, we are going to look at monitoring tags in a RS Logix 5000 processor. So what we're going to do here is we are online with the processor. I'm going to monitor the tags of local:4:data bracket 1.1. So I'm going to open up my controller tags. We're going to close all this out. Close all of this out. We're going to start with nothing up on the screen. Right, we're online with our processor. We're going to open up controller tags. Now we're going to look for that input card, which is right here. And it's an input, so we're going to expand that. We're looking for this address down here. We're going to expand that one. We're looking for input data. And we'll see that if we pull this over here, we can actually see the descriptions. We're in the tag organizer. It's kind of like a spreadsheet, so I can move things around. And I should be able to actually see the bits change. And I can see those change. I can see the stop buttons change. And if I need to, I can edit descriptions, change descriptions from this controller organizer. Here's all my descriptions, matching some of the descriptions on the virtual trainer. We can also look at our tags. If we come over here, I've added some tags for us to look at. We're going to pull up our drill down so we can look at these tags. Go full screen, and we will see that we've added some tags here. And we have a Boolean tag, which is 1 bit. This 1 bit tag here will actually take up 32 bits of memory. Every time we assign a tag or make a tag up, it's actually going to consume 32 bits of memory. So it's always a good idea, if you can, instead of writing your code and making a bunch of different bits, is to make one 32-bit word and use individual bits out of them. We also have a integer file. Notice this one is showing its maximum negative number. This is a negative integer file. There's different types of integer. There's a SINT file, which is 8-bit. Typically, we don't use that anymore, but if we're trying to communicate with a device that uses 16-bit processing, we're going to have to do our calculations in 16-bit and send that data over. Otherwise, it will not understand it. So let's look at how we can look at this. Right now, the style is in decimal, showing the maximum value. We can turn it in binary. We can pull this over, and we can see that this signed integer right here is giving it a negative number. See that 1? This is a signed integer bit, giving it a negative number here. We go here, we'll see that's negative. If I go in here and I change this binary value back to a 0, and then I change the style back to decimal, I'll see that is 0. And so you don't really have to go through calculations and everything on adding binary and everything for the processor. I mean, that's good to know. You can also use your Windows calculator. And we can see that, for example, if we wanted to know what 1101 was in binary, I could use Windows calculator to show that that is the value 13, and vice versa. How I got that was I picked the programming option in the Windows 7 default calculator. That's another handy little hint. Here we have double integer value here, and we'll see that the maximum negative number it can display is in binary here, decimal here. One cool thing, if you play with this a little bit, it helps you understand how these signed integers work, because here we have nothing, right? So we know that this means negative. So what is our maximum positive value in a 16-bit word? We can just type it in, and we'll see change it back to decimal. We'll see that 32,767 is the maximum value. So you can see why 32-bit processing helps us, because the larger the bits that we can store, the 16-bit can handle larger numbers, but it has to chunk this data together when it takes more processing power to chunk these integer words together in one continuous chunk of data to do the calculations. That's why the 32-bit's faster than 16-bit processing, and 64-bit processing is faster than 32-bit processing.